Everyone, go ahead and mute your microphones unless you're one of the speakers or you're asking a question later during the Q&A. If you want to ask questions during the talk, feel free to put it in the chat. So Prasanna and Sujoy, you guys are welcome to pause and answer questions, or we could do all the Q&A at the end. Either way is completely fine.
I think in the end, doing the Q&A will be more.
Yeah, but that might be easier in the virtual setting.
Yeah.
So, just if you have questions, everyone, please post it in the chat. I'll ask them at the end. And but please mute your microphones so we don't have lots of cross clutter. Anyway, let's go and get started. So this is a talk on side channel analysis of Lattice PQC candidates. Really wanted to kind of showcase some recent work in this space and encourage people in the community to look into this area. Even moving forward after the standards process ends, this will still be an important area of research, we believe, going forward. So anyway, our two speakers today are the joint talk from Prasanna Ravi and Sujoy Sinha Roy. The talk title, like I said, is Side Channel Analysis of Lattice-Based PQC Candidates. The abstract is, like classical public key schemes, Lattice-based post-quantum public key schemes, too, are vulnerable to side channel attacks. They're going to be giving a summary of different side channel attacks on Lattice-based PQC candidates and classifying them into broad categories. And then they're going to conclude with design and implementation of countermeasures. Just to introduce themselves, so Prasanna Ravi is a research assistant at Temasek Labs, Nanyang Technological University, Singapore, pursuing a PhD in side channel and fault analysis of lattice-based cryptography. And Sujoy Sinha Roy is an assistant professor in cryptographic engineering at IAIK, the Graz University of Technology. And please go and take it away, guys.
Thank you very much for the introduction. I'm Sujoy Sinha Roy. I'll be presenting side channel analysis of lattice-based PQC candidates together with Prasanna Ravi. Lattice-based cryptography is a generic term. It means constructing cryptographic primitives involving lattices. Construction of a cryptographic primitive and then analyzing its mathematical security is the first step. Then these cryptographic primitives or algorithms, they become practical when they can be implemented on a wide range of platforms, ranging from tiny IoT devices to powerful CPUs or even harder accelerators. Physical security of the implementations is another very important aspect because different physical attacks can be mounted on implementations in different applications. So in this talk, actually, we'll be describing different practical side channel attacks on lattice-based PQC candidates, and we will also be describing some of the countermeasures that can be used to prevent such attacks. Before starting the scientific part of this presentation, I'd like to read this notice. So for our talk, we use published articles from our journals, also conferences and ISER reprint archive articles. As we try to give an overview of this research area, we also include works by other researchers, and we cite them appropriately when we use them. Also, we simplify concepts for easier explanation, and as this is a finite timed presentation, we cannot exhaustively cover all relevant works in this area. We mainly focus on LWE, LWR-based public encryption or key encapsulation schemes, and by side channels, we mean like timing, power, and EM side channels. This NIST PQC standardization project, its first round started in 2017, and now we are in the third round. And in all the rounds, lattice-based schemes, both public encryption, KEM, or digital signature schemes, they are the majority. And this chart shows a classification of the finalist and alternative candidates, of course, lattice-based candidates. And here, interestingly, one thing has happened that in the recent years, there are several side channel attacks on LWE and LWR-based construction specifically. And there are also protected implementations of these categories of schemes. In this talk, we'll be mainly focusing on side channel analysis of LWE and LWR-based public key encryption or key encapsulation schemes. there are I'll be also talking about different countermeasures that can be used to protect them, and some of these countermeasures can be extended to other schemes such as NTRU or even digital signature schemes. But the focus of this talk will be mostly on LWE, LWR-based public encryption and key encapsulation schemes. And this is the outline of the talk. I will first give a background and describe different variants of LWE problem and a public encryption scheme, especially a framework that will be used as an example to describe the attack. Then Prasanna will be describing different practical side channel attacks, both algorithmic level and implementation level. And then we'll be describing masking countermeasures to prevent such attacks. And finally, we'll be drawing conclusions and highlight some of the future directions in this area. So to understand the learning with error or LWE problem, let us recapitulate our school level algebra classes. There we are given algebraic equations with unknown variables x and y, and we're asked to solve the unknowns x and y. And there is also a matrix vector representation for a system of linear equations. This is easy to do because the number of unknowns is really small. And when there are many unknowns, such as n number of unknowns, S1 to Sn, so anything red colored means like unknown or secret, anything green color means public. So here we have n unknowns, and when the number of unknowns is large, then we can use here actually a technique called Gaussian elimination. There can be a computer program for that, and it can solve a system of linear equations as long as the number of independent equations m is greater than or equals to the number of unknowns n. So this is easy. However, the situation changes drastically when small errors ei they are added to the system of linear equations. Then solving the secret in the presence of unknown errors becomes computationally infeasible for classical as well as quantum computers. And this is the learning with error or LWE problem. So you have to learn the secret S in the presence of unknown errors. And this problem has been used to construct efficient lattice-based public encryption and digital signature schemes. Now, there are different variants of the scheme. In case of the LWE, which now I will call standard LWE, we have this matrix A consisting of uniformly random elements. So all the elements here are uniformly random. Now there is a special variant known as ring LWE, where only the first column is uniformly random. And then all the remaining columns, they are generated by megacyclic rotations of the first column. So there is a special structure involved in ring LWE. And in this setting, the matrix vector arithmetic simply becomes polynomial arithmetic. So you can represent all the elements, matrices and vectors as polynomials and do polynomial operations. This ring LWE has resulted in more efficient schemes compared to the standard LWE because it's computationally efficient and it also reduces the communication bandwidth. Then we have module LWE. Module LWE interpolates between standard LWE and ring LWE. It has a hybrid structure. You can see the matrix as well as polynomial representation. So this matrix is consisting of multiple submatrices, and each submatrix is generated from its first column by performing megacyclic rotation. So in this setting, we have matrices and vectors of polynomials. So we perform both polynomial as well as matrix vector arithmetic. Normally, the dimensions of the matrices and vectors are small. And then we also have learning with rounding problem. This is not massively different from learning with error problem. In LWE, the errors are explicitly generated and then added to the system of equations to make it noisy. In case of learning with rounding, errors are not added explicitly, they are generated by a deterministic rounding operation. So what happens here is that you perform this matrix vector multiplication, and then the result coefficients or result elements, they are multiplied by P and then divided by Q, where P is smaller than Q. As Q is larger, there is a data compression operation because there is also a rounding operation, and this rounding operation introduces rounding error to the system of equations. So in LWR, the noise comes from deterministic rounding operation. Similar to LWE, LWR can also be extended to have ring LWR and module LWR variants. Now I'll give an example of a ring LW based public key encryption algorithm. So it consists of 3 routines: key generation, encryption, and decryption. In key generation, it outputs a public key and a secret key. All arithmetic operations are performed in a polynomial ring RQ with coefficient modulus Q. So there is a generator. It expands a random seed and generates a uniformly random polynomial A. Then there is secret distribution from which the secret polynomial S is sampled. The coefficients of this secret polynomial are small. Then there is an error distribution from which an error polynomial is sampled. The error coefficients are also small. And then after polynomial operations, we get a polynomial B, which is like this. And this is a ring LW sample. Okay, and the public key is the polynomial A and the polynomial B. This tuple is the public key. And the secret key is the polynomial S. Now, given the public key A and B, you know it's ring LW problem, so it is computationally infeasible to obtain the secret polynomial S in the presence of unknown error E. Then encryption operation, there is a message M and it is encrypted using the public key to produce a ciphertext CT consisting of 2 polynomials Q and P. And in this case, an ephemeral secret polynomial S prime is sampled, and then there is also an error polynomial E prime, actually 2 error polynomials E prime and E double prime. They are sampled from the error distribution, and then simple polynomial arithmetic operations are performed. Then the first LW sample or ring LW sample is the polynomial U, and then another LW sample is calculated, but it is added with an encoding of the message. So the message M is actually a binary string consisting of zeros and ones, and then these message bits, they are encoded into polynomial coefficients simply by multiplying them with Q over 2. So this 1 0 1 0 becomes Q over 2, 0 Q over 2, then 0. And this encoded message polynomial is simply added with the output of the polynomial arithmetic, and then you get a polynomial V. So you have a ciphertext consisting of U and V, and this V ciphertext is actually masking an encoded message using an LW sample. In the decryption operation, it computes the message back using the secret key escape starting from the ciphertext. So here it performs polynomial arithmetic V minus US, and if you check the equations, you will see that the result of this polynomial arithmetic is a polynomial M prime, which is actually the encoded message polynomial plus some noisy component. And this noisy component, or E small, actually comes from the noises that are involved in the encryption process and also during the public key generation process. And since all the noises are small, actually, then E small also has a small. And when the norm of the E small is small, with respect to the modulus Q, you can perform a simple threshold decoding operation, coefficient by coefficient, to filter out this noise and extract the message bits. So this decoding operation basically takes an input coefficient of the polynomial M prime, and then it checks if the coefficient resides near the 0 or near the Q over 2. If it resides near 0, then the output message bit is 0. Otherwise, 1 is the output message bit. So this is a very simple ring LW based public encryption scheme, and it is chosen. It is CPA, IND CPA encryption scheme. Now I have shown here only ring LW based scheme as an example. Actually, you can have a general framework for public key encryption. So you can extend the ring LW example to have different variants of standard ring or module LWE, LWR based schemes. The fundamental concept remains almost the same, but there are variations. Actually, different PQC schemes, LW or LWR based, they are different based on the type of the problem they use, LW or LWR, or what variant of that, and also in the parameter choices, such as like how you choose the ring dimension or the modulus, from which secret dimension distribution or error distribution you sample the errors and secrets. Also, like if your scheme uses error correcting code or it doesn't use, and there can be also protocol level optimizations, or even there can be specific algorithms. For example, a polynomial arithmetic operation can be done only using a particular type of algorithm or something like that to have better speed. So throughout this presentation, we'll be using the example ring LW public encryption scheme to demonstrate different side channel attacks and also the countermeasures. Now, the public encryption scheme that I described is chosen plaintext attack resistant. It is not CCA or chosen ciphertext attack resistant. So here is an attack, CCA attack, where an adversary tries to extract the secret key from a decryption algorithm. So the adversary has access to this decryption device, and then the adversary creates malicious ciphertext, mostly invalid, by taking care of the features of the decryption algorithm, such that the output of the decryption operation reveals messages that are very much related to the secret key or part of the secret key. In case of a valid decryption operation, valid ciphertext, this message will of course be not related to the secret key, to the plain message. But here with malicious ciphertext, the output message is related to the secret key. Then there is a plaintext checking oracle, and the attacker tries to guess what message is generated. So it queries the plaintext checking oracle, and this oracle tells the attacker if the guess of the attacker is correct or incorrect. In this way, from correct guesses, attacker can build a database and then use the database to reveal or extract the secret key of the decryption algorithm. Here it of course assumes that the secret key is static, it is not changing throughout this attack. Then this attack or CCA attack can be prevented using a transformation that came from Fujisaku and Okamoto. So what it does is basically, instead of producing the output of the decryption immediately, it takes the decrypted message and then performs a re-encryption operation to compute a fresh ciphertext CT prime, and then this fresh ciphertext or recomputed ciphertext is compared with the input ciphertext. Okay, and if the comparison succeeds, then it produces the session key, which is actually derived from the message using a key derivation function. And if the comparison fails, that is, the two ciphertexts are different, then it simply gives a fail or reject symbol. In some schemes, it produces a random garbage. Now this prevents the CCA attacker. So here is an example. This attacker is crafting malicious ciphertext, and after this decryption, it has message which is decryption of an invalid ciphertext, and then re-encryption produces a new ciphertext, but this new ciphertext will be different from the input invalid ciphertext because this is a valid encryption. So this comparison fails, and this algorithm, the entire decapsulation algorithm, doesn't reveal any output. The message is not revealed. It simply gives the reject symbol. In any case, fail or pass, the message is directly not revealed. So what is happening here is that in the previous case, the attacker had this plaintext checking oracle as an assistant, and this Fujisaku-Okamoto transformation simply removing that plaintext checking oracle. So the CCA attack can be prevented with FO transformation. Now the question is, can an attacker use side channel information to guess the messages? So this brings us to the idea of chosen of side channel assistant chosen ciphertext attacks. So here the attacker uses side channels to know information about the message. So basically, the side channels are used to instantiate the plaintext checking oracle within the decapsulation routine. So in the next part of the talk, different attacks using this model will be presented by Prasanna. So now, yeah, Prasanna will continue with it.
Yeah, I hope you're all able to hear me. Yeah.
Yeah.
Okay. So I'll continue. So thanks, Sujoy, for the introduction. So several side channel attacks have been proposed which operate in the chosen ciphertext setting to perform key recovery in LW and LWR based schemes. And we broadly classify the attacks into two categories. One, the attacks that work at the algorithmic level, as well as at the implementation level. Now, algorithmic level side channel attacks are those which primarily exploit algorithmic features of the LWE or LWR based PKE framework and are relatively agnostic to the implementation platform. However, the implementation level attacks are those that primarily exploit properties of the target implementation. So we lay more focus on the algorithmic level attacks as they really give us a deep and intricate understanding of the properties that are actually inherent in the PKE framework that make them vulnerable to side channel attacks. So we start off with the algorithmic level. So we basically start off with the algorithmic level attacks, and in particular attacks that operate in a chosen ciphertext setting. So as we go through the different attacks in this talk, we'll also attempt to classify these attacks into different categories. So as we go through the different attacks in this talk, we will attempt to classify these attacks into different categories based on the different attack approach and objectives. So we will be coming back to this classification chart time and again during the presentation. So the idea of using side channel analysis to assess chosen ciphertext attacks in the context of LWR based schemes was first proposed by Bauer et al. However, it was Dianos et al. Who performed the first concrete attack on two schemes, LAC and Ramstick, where they exploited timing side channel coming from variable time runtime of error correcting codes. And subsequently, it was Ravi et al. Who generalized the attack approach to constant time implementations of multiple LWR based schemes using the EM side channel. So let's see how this plaintext checking oracle attack works. And this attack primarily consists of two parts. Part 1 deals with how an attacker constructs the malicious ciphertext to carry out the plaintext checking oracle attack. And part 2 deals with how an attacker performs side channel analysis to obtain some useful information about the sensitive decryption output for the malicious ciphertexts. So to understand the construction of the malicious ciphertexts, we need to go back to the decryption procedure here. So we have two ciphertext components, U and V, which an attacker is free to choose. So let us choose U with the following structure, where only the first coefficient is non-zero with a value of k, and all the other coefficients are actually zeros. So the product U times S is nothing but a scalar multiple of a secret S with k, where S0, S1, S2, and so on are the secret coefficients. And then we also choose V with the same structure as U, where the first coefficient has a value of p and all the other coefficients are actually zeros. And now these are the coefficients of the encoded or the encoded message polynomial. So we can see that each coefficient is actually only dependent on the corresponding coefficient of the secret. So the first coefficient depends on S0, the second coefficient depends on S1, the third on S2, and so on. So in this situation, an attacker can actually choose values for the constants k and p in such a way that the first bit of the message is a function of the first secret coefficient S0, while all the other message bits are actually fixed to 0. So in this way, the attacker can restrict the message to take only two values. It's either all 0, which we denote as case O, or all 0 with a 1 at the LSB, which we denote as case X. So by choosing a specially structured ciphertext, we've essentially reduced the dimensionality of the problem from n dimensions to a single dimension, and the message here is only dependent on a single coefficient S0. Now the attacker can choose concrete values for the tuple k and p to build a binary distinguisher for the secret coefficient S0 based on the two classes O and X. Now this is a table for a parameter set of round 5 where S is a ternary polynomial and S0 has three possibilities. And if the attacker has the knowledge of whether a given ciphertext query resulted in a decryption output of either O or X, then he can actually recover S0 with just two ciphertext queries. So now that we know how to recover a single coefficient, this technique can be extended to recover the full secret polynomial one coefficient at a time in the following manner. So as Sujoy mentioned, most LWR based schemes, especially the efficient ones, involve computation over polynomials and efficient polynomial rings, which have special rotational properties for polynomial multiplication. And multiplication of a polynomial with x bar I essentially rotates the polynomial by I locations, either in a cyclic or anti-cyclic or negacyclic fashion, depending on the ring in which you're operating on. So by simply changing the location of the non-zero coefficient of U, the message m dash depends upon different secret coefficients. So for example, this particular choice of U and V ensures that the message is dependent on the n-1th coefficient of S, And this particular choice ensures that the message is only dependent on the n-2th coefficient of s and so on. So in this way, the attacker can simply change U and recover different secret coefficients one at a time to perform full secret key recovery. So we observe that this rotational property, however, is not present in schemes such as schemes based on the standard LWE problems such as Frodochem, but the attack can still be performed in the following manner, where we fix U, but we change the location of the non-zero coefficient of V, and by doing that, we also change the location of the secret dependent message bit, and we'll still be able to perform the attack, but then the attacker has now more than two classes to actually distinguish. So the attack still works, but it's slightly more complicated. So yeah, we can actually see that this technique is generic and it purely exploits the algorithmic properties of LW and LWR based PKE framework. So all the attacker needs is to distinguish between the two cases O and X to perform full secret key recovery, which actually brings us to the second part of how an attacker can differentiate between the two classes O and X using side channels. So Dianos et al. Exploited a variable runtime of error correcting codes in LAC and Ramstick, where O is a valid code word and X is actually an invalid code word, and hence decoding O takes much lesser time than decoding X, which is an invalid code word. So decapsulation of ciphertexts corresponding to class O takes much lesser time than decapsulation of those corresponding to class X. And this differential timing behavior can be exploited in the following manner. So the attacker first creates side channel templates for the two classes O and X. In this case, they are just timing templates. And once the templates are generated, the attacker simply queries the target device, the decapsulation device with the malicious Trojan ciphertext, and classifies each ciphertext as either class O or class X. And subsequently, the attacker can then use this O or X information to recover the full secret key. So while this attack can be thwarted using constant time implementations, Ravi et al. Showed that EM or power side channel can be used to target constant time implementations as well. So they identified several vulnerable operations which leak information through the EM side channel. So for example, decoding of O and decoding of X involve very different computations, resulting in several different leakage points which an attacker can easily exploit using simple template matching techniques. And for schemes which do not use error correcting codes, computation within the effort transform can be targeted. So for example, hash of the message 0 with PK and hash of the message 1 with PK involve very different computations which can be easily distinguished through side channels. So please note that this particular attack does not directly target the decryption output, but rather it targets the computations over the decryption output. And these computations, in these computations, there is enough diffusion because of the single bit change, which can be easily distinguished through side channel information. So here are some experimental results for the attack complexity on different schemes, and the numbers are taken from the EM attack of Ravi et al., where they target implementations from implementations of these schemes on the ARM Cortex M4 microcontroller. And as you can see, the attack can be done in a few thousand traces, and the total attack time is only a few minutes, which shows the effectiveness of the attack. And one of the main advantages of the attack is that it does not really require a sophisticated SEA setup, because there are many leakage points, and the SEA is essentially a simple two-class classification problem for which simple templating techniques are actually sufficient. So the attack is robust to SNR, and the attack is also performed in a non-profiled manner, and hence the attack can directly be performed on the target device, and there is no requirement for a clone device. So in terms of countermeasure, masking serves as a strong algorithmic countermeasure against this attack, since the countermeasure splits the message or operation over the message into two random shares. So the easy classification through SEA, as we did earlier, is no more possible. And Sujoy will later present a detailed overview of various masking countermeasures for LW and LWR based schemes. So we now attempt to make a classification diagram for side channel attacks on LW/LWR based schemes that primarily operate at the algorithmic level. So we classify the PC Oracle based attack, which is the plaintext checking Oracle based attack, as one category of key recovery attacks that work in a chosen ciphertext setting. So a few observations on the PC Oracle based side channel attack. So we saw that key recovery can be performed in a few thousand traces, but though this number is still low, we can always ask ourselves if we can do better with much fewer traces. And turns out that it's possible to do that, and for that we need to take a deeper look at how the PC Oracle based attack works. So if we look at the final decrypted message of the PC Oracle based SCA, we can actually see that we are limiting the message to just two possibilities, and there is only a single secret dependent message bit, and all the other message bits are actually fixed to 0. So a natural question we can ask ourselves is if we can use all the message bits. So let's say if we have an attacker who has the power to precisely recover all the message bits, can we do a more efficient attack? And this is what we refer to as a full decryption oracle, where an adversary has full access to the decrypted message, not just the ability to classify, but obtain full knowledge about all the message bits. And this brings us to the idea of a full decryption oracle based SCA. And to exploit the full decryption oracle, we need to choose a different value for V. And we choose a V such that all the coefficients of V are actually fixed to a constant value of P. So the resulting M dash, the message polynomial, looks something like this. And now an attacker can choose values for the tuple K and P in such a way that every message bit actually depends on the corresponding coefficient of the secret polynomial. So for example, the message bit M0 depends on the secret coefficient S0, message bit M1 depends on S1, M2 depends on S2, and so on. So every message bit can be used as a binary distinguisher for the corresponding secret coefficient. So compare this to the previous PC Oracle based attack, where we target one coefficient at a time. Here we are able to do a simultaneous attack on all the coefficients at the same time. So using clever choice of the ciphertext, what we have done is we have reduced an n-dimensional problem into n simultaneous 1D problems, which are much easier to solve. And Zhu et al. Proposed an FD Oracle based side channel attack on Kyber, wherein full secret key recovery for Kyber 512 was possible in just 8 chosen ciphertext queries. And this was subsequently improved to 6 chosen ciphertext queries by Ravi et al. In another work with a very minor optimization. Thus, we can see that an attacker with access to a full decryption oracle can actually perform a much more powerful attack, which only requires a few handful of traces to perform full key recovery. And more recently, Ngo et al. Proposed improved techniques for key recovery, which work even when all the message bits are actually not recovered correctly. And they actually demonstrated a key recovery on Sabre using just 16 chosen ciphertext queries. And as we can see, this attack also works at the algorithmic level and thus applies in a similar manner to different LW and LWR based schemes. So in our classification chart, we place FD Oracle based attacks as another category of side channel based key recovery attacks that work in a chosen ciphertext setting. While the PC Oracle based attack, which operates with binary information about the message, requires a few thousand traces, the full decryption Oracle based attack works with complete information about the decrypted message, but only requires a handful of traces. So we have a very nice trade-off here. So the next question that comes to our mind is, how does an attacker actually perform full message recovery through side channel analysis? And what is that critical liability or vulnerability that is present in LW and LWR based schemes that enables full message recovery in the first place? So this brings us to our analysis of the message encoding and decoding functions. As seen earlier, they are actually crucial blocks in the encryption and decryption procedure that are used to convert a message in a bit vector representation to a polynomial and vice versa. And this encode and decoder function is actually very unique for LW and LWR based schemes, and it's not present in traditional ECC or RSA based schemes or even other type of post-quantum schemes. And this encoding and decoding is done in a bitwise fashion and involves bitwise manipulation of the message. And this bitwise manipulation of the message is shown to have side channel leakage. So here we have a toy message encoding example with 5 bits, where each bit is encoded into a corresponding coefficient and then it's stored in memory one at a time. And an easy observation that we can make here is that there are only 2 possible types of operation for each bit, where a 0 is encoded to 0 and a 1 is encoded to q by 2. And this behavior leads to easy side channel leakage both during computation as well as during storage of the encoded coefficients. And Amiat et al. Were the first to exploit this kind of leakage present in the message encoding operation, and they actually demonstrated a single trace message recovery attack on New Hope using simple template matching techniques. And this is actually a power side channel trace from an unoptimized implementation of New Hope on the ARM Cortex-M4 microcontroller. And as you can see, using simple visual inspection, we are able to classify a bit into either 0 or 1. However, leakage is much less pronounced in more optimized implementations, but single trace message recovery was still possible. And subsequently, Sim et al. Generalized the same attack to multiple LW-LWR based schemes, and all the attacks only required a single trace for full message recovery with a very high success rate. And on first thought, this type of leakage seems to be coming directly from the implementation and seems to be easy to fix, right? And one can think of many ideas to actually fix this. So for instance, one idea would be to simply parallelize the encoding procedure using vectorization features available in software platforms, and it's also trivial to perform in hardware as well. And as a result, you have simultaneous leakage coming from multiple bits, but it at least removes leakage from individual bits, preventing message recovery. And the next idea that one can think of is to simply shuffle the order of encoding of the message bits. And by shuffling, you are not really removing the source of leakage. So an attacker can still recover the individual message bits, but not its correct order. So if there is enough entropy in the shuffling order, then this particular idea also thwarts message recovery. And one can also come up with more such techniques to actually thwart the attack. And we need to think if these techniques actually really offer protection. And turns out that the problem actually runs deeper, and it's not an implementation issue that can be patched using implementation level fixes. And Ravi et al. Actually showed that one can use ciphertext malleability property of LW and LWR based schemes, and this ciphertext malleability property can be used as a powerful tool to enable improved side channel attacks for message recovery, even when concrete protection mechanisms are actually employed. So let's try to understand ciphertext malleability in LW and LWR based schemes. And in order to do that, we need to again go back to the way decryption works. So in decryption, there are two main components. One is the product of U times S, and the other is the ciphertext polynomial V. And if you look at the product U times S, there are two terms where the first term A times S times S prime is large, and the second term E prime times S is small. And if you look at the ciphertext polynomial V, then we have the same large term A times S times S prime, followed by the encoded message, followed by two small error terms. Now the decryption procedure basically subtracts U times S from V, and by doing that, we are essentially subtracting or removing this large error term, and we end up with the encoded message with a few error terms. And this encoded message polynomial is then decoded back to the message. So here, if we observe how the message is manipulated during decryption, it leads to a few key observations. So firstly, the message is only additively hidden within the ciphertext component V. And during the decryption procedure, there is no diffusion of the message polynomial whatsoever. So each coefficient Vi only determines the corresponding message bit Mi. So this is the key observation we make here. And let's say we have a valid ciphertext polynomial V, and let's say we add Q by 2 to the ith coefficient of V. And if we do that, what happens is we are also adding Q by 2 to the ith coefficient of the encoded message polynomial M dash. Now let's try to visualize the decoding of the ith coefficient of M dash. And let's say if this is the original value of the ith coefficient, then if we add Q by 2, then we are pushing this value beyond the boundary, and hence we flip the message bit from 1 to 0. And similarly, the same also works in the other direction as well. So essentially, by adding Q by 2 to the ith coefficient of V, we are actually flipping the message bit. And turns out that the attacker can flip any number of message bits simultaneously, and this fine-grained ciphertext malleability property can be used as a powerful tool to perform improved side channel attacks. So let's look at the first idea that we propose, which is the parallelized message encoding procedure. And for example, we consider a 4 times parallelization. So in step 1, what we do is we query the decapsulation device with a valid ciphertext. And let's say all these messages with 0110 are manipulated simultaneously. So we have leakage coming from the compute of 0110. And we could also have leakage coming from the storage of 0110 as well. So we denote it as T1 and T2. And just to make it clear, the target here is the message encoding operation during re-encryption. So this operation is available in the decapsulation procedure. And in step 2, we create a modified ciphertext V dash, wherein we simply add Q by 2 to the first coefficient of V. So we basically try to flip the first bit. So the first bit will be flipped from 0 to 1. And when we observe the side channel leakage, we have leakage coming from the compute of 1110. And we have a leakage coming from the storage of 1110. And we denote the modified leakage as T1 dash and T2 dash. And in the third and final step, we basically compare the two leakages, T1 and T1 dash. And by observing the change in leakage, we can actually infer the value of the bit flip. So if the leakage T1 dash is more than T1, then we know that the bit flip is actually performed in a positive direction, and hence the original value of the bit was actually 0, and we can do a vice versa inference as well. And we performed the bit flip only for a single nibble here, but the attack can actually be simultaneously done on all the nibbles of the message. And hence, if we have a 4 times parallelization, irrespective of the number of bits in the message, full message recovery can be run in just 5 side channel traces. And if you have an n times parallelization, full message recovery can be done in n plus 1 traces. And the main assumption we have here is that given a side channel trace, an attacker can recover all the individual message bits in a single side channel trace. So it turns out that the parallelized encoding procedure does not really offer protection against the attack. And let's look at shuffling, which can also be defeated in the same way. So in step 1, we query the decapsulation device with a valid ciphertext. And then we use sidechain analysis to retrieve all the bits, individual bits of the message. And since shuffling does not affect the Hamming weight, we simply compute the Hamming weight of the retrieved message, which means just count the number of 1 bits in the retrieved message. And the Hamming weight is denoted as X dash. And in step 3, we create a modified ciphertext to simply flip the first message bit. So we are adding Q by 2 to the first coefficient. And again, we do SCA to retrieve all the bits from the leakage and let the modified Hamming weight due to the bit flip be X double dash. Now, an attacker simply compares the two Hamming weights X dash and X double dash and infers the original value of the message bit. So if you have K bits in the message, then message recovery can be done in K plus 1 traces. The typical length of the message is 256 bits, so message recovery can be done in 257 traces. And turns out that shuffling is also not a strong countermeasure. And this is primarily because of the ciphertext malleability that's available in the LW and LWR base schemes. And the attack can also be extended to masked implementations, albeit with a higher number of traces, depending on the type of implementation we are dealing with. And though we completely only looked at the message encoding procedure, turns out that the attack can also be applied to the message decoding procedure as well. And as we can see, the protections that we just saw now only increases the attacker's complexity, but really do not prevent the attack completely. So as far as the countermeasures are concerned, the combination of shuffling and masking is considered to be secure as of now. But this is yet to be analyzed in detail by any existing work. And with respect to advantages, we can see that the attack is very effective because it can perform full message recovery in very few traces, and the attack is also adaptable to different protection mechanisms as well. But the attack has a few downsides, especially with respect to implementation. So the attack actually requires a relatively high SNR. Because here we are actually targeting individual bit manipulations which involve identification of very precise leakage points. So we have much lesser leakage points here, and hence we require a high SNR to mount a successful attack. And the attacker can also, in fact, the attack can be made more effective using a more sophisticated setup which employs techniques like trace filtering, resynchronization, using more advanced EM probes, and so on. So as we can see, the leakage from the encoding and decoding procedure, along with ciphertext malleability, can be used to perform improved or enhanced side channel attacks for message recovery on LW and LWR based schemes. And now we go back to our attack classification chart and we add a new branch of attacks called the message recovery attacks. And we add the attacks on both the message encoding as well as the decoding procedure. And leakage from this message encoding and decoding procedure can be used to instantiate a full decryption oracle to carry out the full decryption oracle based key recovery attacks. So now let's look at the decapsulation procedure, and the different attacks that we just mentioned target these two blocks within the decapsulation procedure. So we are pretty sure that these two blocks should definitely be hardened using strong side channel countermeasures. So this leaves us with the final comparison block, and the obvious question that comes to our mind is whether this comparison block actually contains any sensitive information that is interesting for a side channel attacker. So in order to do that, let's try to first analyze the operation of the comparison block. So we know that for a valid ciphertext, the comparison always passes, and for invalid ciphertext, the comparison always fails. So we know that the comparison always fails for all the invalid ciphertexts, and at the outset, it seems like this block hence might not have much for a side channel attacker. But turns out that it's not the output of comparison that has information about the secret key, but rather how comparison fails that could potentially leak information about the secret key. And this can actually be exploited using what we call as decryption failure based attacks. And such an attack in a side channel context was actually proposed by Go et al. And this brings us to the final category of attacks which we'll cover in this talk, which is called the decryption failure oracle based side channel attacks. And let's try to understand how it works. So we first construct a valid ciphertext for a random message M, and let's try to visualize the decoding of a single ith message coefficient M dash of I. And let's say the actual value of M dash of I is somewhere here in the integer ring. Now we simply add a small error to the ith coefficient of V and observe the corresponding change in the message M dash. Yeah. So let's say we add an error of 1 to the ith coefficient of V, and this will introduce a corresponding perturbation in the ith coefficient of M dash. But in this case, the perturbation is not large enough to push the value beyond the boundary, so the message output still remains the same. So as you can see here, we are again using ciphertext malleability, but in a more fine-grained manner. So we continue to keep adding errors until we hit a point where we have a bit flip, and hence we have a decryption failure at the ith bit. And when we have a decryption failure at the ith bit for a certain perturbation, in this case for a perturbation of 4, we have a decryption failure at mi, then this supposedly gives information about the ith coefficient of this error polynomial es. Now turns out that this particular error polynomial es is actually a secret dependent error polynomial and is linearly dependent on the long-term secret s. And hence, through decryption failures, an attacker actually obtains linear hints about the secret, and provided the attacker has enough number of hints, then this potentially reveals the complete secret key. So now we know that provided the attacker can induce decryption failures and identify decryption failures, he can perform key recovery. But the next question that comes to our mind is, how does an attacker identify decryption failures through side channels? And turns out that the ciphertext comparison block actually leaks information about decryption failures. So let's again try to visualize the decapsulation procedure. And for a valid ciphertext here, the comparison block, there'll be no difference between the recomputed ciphertext and the input ciphertext. So yeah, basically there'll be no difference. And let's say we add a small error to the ith coefficient, and the error is not large enough to induce a bit flip, and hence the message stays the same. And if the message stays the same, then the recomputed ciphertext and the input ciphertext are mostly the same, except for a single coefficient difference at the ith coefficient, because the attacker only created the perturbation at the ith coefficient. So most coefficients are actually the same when there is no decryption failure, and only one coefficient is actually different. So this behavior remains the same when there is no decryption failure, and immediately there is a decryption failure at, let's say, the ith position. I'm sorry, there is a typo. This is actually a flip of mi, where we have a flip at the ith position. Then this single bit flip induces diffusion, because there are several hash functions used during re-encryption. And because of this single bit flip, the recomputed ciphertext will actually be vastly different from the input ciphertext. So in the comparison block, almost all the coefficients will actually be very different with a very high probability. So the behavior that we observe is that if there is no decryption failure, then there is only one coefficient that is actually different. But if there is a decryption failure, then almost all coefficients are actually different with a very high probability. And this particular behavior can be observed through side channels, and an attacker can actually instantiate what we call as a side channel based decryption failure oracle to perform key recovery attacks. And Guo et al. In Crypto 2020 presented the first decryption failure oracle based attack in a side channel context on FrodoCam, and they performed a timing attack targeting a non-constant time comparison which immediately aborts when comparison actually fails. So if there is a decryption failure, then the comparison immediately aborts because both the ciphertexts are actually very different, and hence it takes a lesser time. And if there is no decryption failure, then the comparison only aborts at the ith coefficient, and provided the ith location is towards the end, then the process takes more time, and hence this differential timing behavior can be exploited to actually instantiate a decryption failure oracle based oracle and to identify decryption failures. And for the attack, they actually required about 2 power 30 decapsulation queries for full secret key recovery across different variants of FrodoCam. And this number also includes retries to get a cleaner timing signal. So if you have a clean timing signal, the actual number could be much lower. And there are also several different approaches known for efficient mask ciphertext comparison proposed by Oder et al. And Bash et al. And these mask ciphertext comparison techniques actually share a common trait. So what they do is, for efficiency, they actually perform checks on partial ciphertexts, and they actually unmask the results of these partial ciphertext checks under the notion that they don't contain any sensitive information. But turns out that unmasking result of partial checks actually leaks information about the decryption failures, which was actually identified by Basson et al. In a very recent work. So these are some of the experimental results from their work, and they actually show that the security of Kyber drastically decreases with the number of approximate equations built using side channel information. And as we know, Kyber actually adopts compression of ciphertext. So when there is compression of ciphertext, then an attacker cannot build exact equations, but can only build approximate equations about the secret key, and hence the security decreases much less. The decrease in security is much lesser compared to when there is no compression. But the decrease in security is not high, but it's still but then the security that's available is still low enough for a potential quantum adversary to actually take advantage of. So this attack is actually pretty serious. And so the takeaway from this work is that we need to implement constant time comparison, and the comparison has to be implemented in constant time. And with respect to masked implementation of ciphertext comparison, we should not actually unmask partial checks. So now that we know that the comparison block also contains sensitive information about the secret key, it also has to be sufficiently hardened against using strong side channel countermeasures. So now we add the decryption failure attack as another category of key recovery attacks. And as we saw, the decryption failure oracle based attacks worked with leakage coming from the ciphertext comparison block. But this attack can be made more efficient if we feed in leakage from the message encoding and decoding procedures. This is an interesting possibility to explore in the future. So now that we've had a look at different attacks that operate at the algorithmic level on LWR-based schemes, let us now think about how to defend against these attacks. So the PC oracle-based attacks can be defeated using masking, and the message recovery attacks on the encoding and decoding procedure can be defeated using a combination of masking and shuffling countermeasures. And the same also applies for the full decryption oracle-based attacks, which primarily derive leakage from the message encoding and decoding procedures. And as far as the decryption failure oracle-based attacks are concerned, properly masking the ciphertext comparison can actually prevent this attack. So as you can see, masking is an important countermeasure. Along with shuffling, can actually defeat most of the algorithmic level chosen ciphertext attacks. And now I'm passing the stage to Sujoy, who will present a detailed overview of masking countermeasures and challenges with respect to implementing masking for LWE schemes. Yeah, over to you, Sujoy.
Thank you, Prasanna. Okay, so I have the control. Yeah, okay. Yeah, I think I have control. Yeah. So what is the masking countermeasure? So masking is a countermeasure against differential power analysis or DP attack. It is widely used by different cryptographic algorithms for protection against DPA. The idea is to randomize computation. So a DP attacker actually observes calculation involving a long-term secret. So the secret is static, is residing, and then uses side channels to gain information about the secret over multiple runs. So the idea of masking is to randomize the entire computation such that the leakage coming out of the device always randomizes every run. So here, the secret S, for example, S is split into multiple shares, S1 to Sk, and then instead of evaluating some function, secret function, for example, decryption, directly on the secret S, this somewhat related function, say f prime, is evaluated on the shares independently. And then the beautiful thing is that the outputs of these independent evaluations, when they can be combined, the result is actually evaluation of the original function f on the secret information f. The idea is related to secret sharing. You share a secret into multiple random looking parts, and then you perform the computation. Now, in case of a first order masking scheme, the secret S is split into two shares, S1 and S2, and then there are two evaluations. So the execution time roughly doubles in most cases. Now, the assumption is that an attacker, the DP attacker, can observe at most one share at a time, cannot observe two shares. Now, there is a second order DP attack, which basically probes or observes two shares simultaneously. So a second order DPA attack can be effective against first order masking scheme. Or to protect a cryptographic implementation from second order DP attack, you need to incorporate second order masking, while the secret S needs to be split into three shares. So it's basically the concept is that as long as an adversary can only have a proper subset of the secret information, then he or she cannot gain full information about the secret S. So using higher order DP attacks, always you can beat lower order masking schemes. But the thing is that the cost of higher order attack always increases exponentially with the order of the masking. Now, there are two types of shares, arithmetic and Boolean shares. In case of Boolean share, the secret is split bit by bit. So here S is a secret bit and it is split into multiple bits. And to combine all the bits, all the shares, you basically have to perform XORs, bitwise XOR operation. So it's addition modulo 2 to get back the original secret bit S. And this procedure is applicable to words because you can generalize word as a vector of bits. So you need to apply this bit by bit to a word. And in case of arithmetic share, you split a secret into random looking values in modulo p, where p is greater than 2. So you basically perform integer additions of all the shares and then perform a modular reduction with p to get back the secret S. Okay, so cryptographic algorithms that deal with Boolean variables, for example bits, they are more friendly to Boolean shares. Cryptographic algorithms that are arithmetic involved, they perform arithmetic shares. And there are some cryptographic algorithms where you need both of them. Okay, so now the question is how to apply masking to lattice-based public encryption. So we take the example of ring LW public encryption. Here, is the decryption operation, and it uses a secret polynomial S. Now, the goal of an attacker is to extract information about the secret using DPM. So the masking idea is to split the entire computation by splitting the secret into random shares, and that will randomize the computation. Okay, so how that is done? The first part is polynomial arithmetic in ring LWN decryption. So you perform polynomial multiplication and subtraction. So in this case, if the secret S is split into two arithmetic shares, S1 and S2, in this way, then you can have a randomized decryption like this. There are two branches. The first branch uses S1 and the second branch uses S2, and these two branches are independent of each other. And of course, when you combine the two shares M1 prime and M2 prime by adding them, you get the original M prime polynomial back. So this works, and this is basically arithmetic masking. And then now the question comes, like, how to perform the decode operation. The previous decode operation, which was for unmasked implementation, takes only one input and produces a message bit by performing a comparison with respect to the modulus Q. So question is how to apply this decode to the shares. So this is mask decoding. So what we want basically is to create or produce a mask and message pair M1 M2 such that their addition over module 2 is the original message bit n. And this has to be computed from the two shares M1 prime and M2 prime in such a way that their combination doesn't leak any information about the original message. And there are actually several ways to design secure mask decoders. So I will describe the first work, RRVV15, which was published in CHES 2015. And this work is based on an observation. The observation is that to perform the decoding operation, you do not need full information about the two shares. So you just need some information, basically where the two shares are located in this modulo Q ring. And that information can be used to simplify the mask decoding operation. For example, if you know that one share is residing in the range 0 to Q over 4, and the other share is residing in the range Q over 4 to Q over 2, then their sum M prime must be in the range Q over 4 to 3Q over 4. And in that case, this M prime will be decoded to a message bit 1. So using the location information, basically where a share resides, you can obtain the decoded message. And so there is a huge compression. You do not need the full information about the two shares, just some locational information. And this is used to design a quad function in this work, RRVV15. So the entire ring is split into 4 quads, 1, 2, 4. And then this quad function, it takes an input share, say M prime, and it outputs the quadrant where this share is residing. For in this case, if M1 prime is the input, then it will give quadrant 1 as the output. For the other share, it will give quadrant 2 as the output. And then there is a rule check. So the rule is that when the two quadrants, basically the two shares, if they are residing in two adjacent quadrants, then you can successfully decode. So here are 4 possible cases where the two shares are residing in two adjacent quadrants. This is a hit of the rule, and you can have a decoding. Now, what if two shares they reside in non-adjacent quadrants? Then this approach fails. And as a solution, an iterative approach is presented in this work. So they basically use a public table consisting of constants delta I, and then they refresh the two shares. So delta I, at ith iteration, a constant delta is picked from the table, and then it is subtracted from one share, and then it is added to the other share. So this refreshes the two shares. The goal is to move the shares in such a way that at some point in time, they reside in two adjacent quadrants, and that is the target of this. So in that case, you can have a valid decoding operation, and this refreshing is iterated over, say, a finite number of times, and that can be implementation specific parameter. So now the next thing is that you have this mask decoding, and what is the final result? So in RRV 15, a masked ring LW public encryption or decryption was implemented, and it was found that if you implement the things in hardware, then you can have some optimization, for example, parallel processing, and the overhead of the masking is only 2.7 times. Whereas in case of software implementation, such as implementation on ARM Cortex M4 microcontroller, the overhead is 5.8 times. And there is another limitation. It comes due to decryption failure. So the problem in this approach is that even after trying for several iterations, it may happen that the two shares are not in adjacent quadrants, and in that case, this decoding approach will fail. So there is a failure probability involved. And the question is, what causes the overhead in the computation time? This overhead comes from two operations. One is polynomial arithmetic. In case of unprotected implementation, you have only one polynomial multiplication, whereas for a first order masked implementation, you have two branches. So the polynomial arithmetic cost roughly doubles, and then you have an iterative quad-based decoding operation, which increases the computation cost further, and also introduces decryption failure problem. So this masked decoding is then improved in the work by OSPG in CHES 2018. So I'll just present the idea. So assume that the two shares that need to be decoded are Boolean shares. So M1 prime and M2 prime, if you XOR them, bitwise XOR, then you get the original M prime back because they are Boolean shares. Now, as this is like bitwise operation, there is no carry propagation involved when you combine the two shares. And in such a scenario, the most significant bits of the original secret M prime are basically determined by the most significant bits of M1 prime and M2 prime. So you basically XOR the most significant bits of them, and you get most significant bits of M prime. So that means, and these most significant bits are basically useful for performing the threshold decoding operation. So that means you can apply the threshold decoding individually to the two shares, and then produce a mask and a message pair. So this is a nice idea. Now the question is how to apply this mask decoding to ring LW public key decryption. The problem there is that the output of polynomial arithmetic is consisting of arithmetic shares. So you do not have Boolean shares. So in OSPG 18, these arithmetic shares are converted into Boolean shares by applying an A to B transformation. So this is the high level diagram. So let us assume that the two shares, M1 prime and M2 prime, they are arithmetic shares and they are modulo from 2 to the power k. Okay, so its power of 2 modulus is used here. And
hey, Sujoy, sorry, I was going to say we're about 10 minutes over time, which is fine.
Okay.
But I was going to say go ahead and maybe wrap it up in a couple minutes.
Yeah, okay.
Just,
maybe I'll take 5, 6 minutes
to
wrap it up. Thank you very much. And yeah, arithmetic to Boolean transformation is applied, and then you get two Boolean pairs, and then you simply pick the two most significant bits from them. So yeah. Now, what if the modulus q is not a power of 2? Then you need an additional block, which is transform power of 2. It basically transforms the arithmetic shares modulo q into arithmetic shares modulo 2 to the power l, and then you can apply the arithmetic to Boolean transformation to get the two Boolean shares. Okay, and so that was the idea of using arithmetic to Boolean conversion and simplify the mask decoding operation. Now, as a case study, I will present some results for masked implementation of SaberChem. Why I chose this? Because to my knowledge, this is the only masked implementation of a NIST PQC final. Saber is based on the learning with rounding problem, actually module version of it. And in this case, as it is LWR, you do not have to generate the noise values or error values explicitly. So there is less noise generation. And Saber also uses power of 2 moduli P and Q. So this rounding operation basically becomes simple bit shift. So this is the high level protocol of Saber. So if you have understood the ring LW encryption scheme, then it is not difficult for you to understand this. The only difference is that here you deal with matrices and vectors of polynomials. And there are of course some in-specific optimizations. Okay. And this operation involves basically like polynomial arithmetic operations and also rounding, which are basically bit shift operations. And you can have a CCA secure KEM by applying a Fujisaki Okamoto transform. And to protect the full decapsulation operation, you need to protect not only the decryption, but also the re-encryption and also the ciphertext comparison operation. So the building blocks that you need are basically you have to protect polynomial arithmetic, and this is easy to do using arithmetic sharing. You have rounding, which is bit shifting, and Boolean shares will be helpful for masking rounding operation. And then you have Keccak-based hash functions and expandable output functions set. So you can use existing masked implementations of Keccak. And then you have binomial sampling for generating the ephemeral secret. So you have to protect that as well. And finally, you also have to protect the ciphertext comparison operation. So the rounding, I'll just cover the rounding and the binomial sampling operation in mask saber. So here, if we have like two Boolean pairs, say x1 and x2, then we can actually have a shifted version of the original x value by k bit simply by shifting the two Boolean pairs, because there is no carry propagation involved when we combine the two pairs. However, in case of saber, the rounding operation is performed on the outputs that are coming from polynomial arithmetic. So the input to the rounding operation or the bit shifting operation are arithmetic pairs. So the idea is to apply arithmetic to Boolean transformation, make them Boolean, then perform the shifting operation, and finally again bring the result back to the arithmetic share by applying B to A transformation. This work by BDKVG actually proposes an optimized way to do it by combining all the three steps together, and this results in lesser cycle count. And then comes the binomial sampling. This binomial sampling takes two pseudorandom strings x and y, and it involves Hamming weight calculation, which is basically a summation of the bits, and then it requires a subtraction operation to produce a sample. You can see that these are like additions and subtraction operations, so they can be masked if we use arithmetic sharing. Now there is a problem. The pseudorandom strings x and y, they are generated by Keccak. So if we use a masked Keccak, it produces actually Boolean shares. So x1 and x2, there will be Boolean shares here. Hence, you have to take care of it. Actually, this paper, BDKV20, it performs the binomial sampling by evaluating half-adder and subtractor circuits on Boolean shares. So what they do is they write down the Boolean expressions for the entire calculation, and then this is a circuit representation, and then they evaluate the circuit on the Boolean shares directly. And on top of that, they also perform bit slicing to improve the performance. So here are some results from that work. So they found that the decapsulation operation with masking is only 2.5 times slower than the unmasked implementation, and overall cycle count remains below 3 million cycles in ARM Cortex-M for microcontroller. The memory requirement increases by a factor of 1.84. So now the question is like, what helps masking in saber? Actually, it is due to two reasons. First thing is it uses power of 2 moduli that makes arithmetic to Boolean conversion easier, and then saber is based on LWR, which implicitly generates error by rounding operation. So you do not have to protect too many binomial samples. So that's it. And now there are also preliminary hardware results from my team. So this is a joint work with Andrea Bosso and Lucas Prokop, and we have implemented masking for saber in hardware, and we did some hardware specific optimization. So we found that so the decapsulation overhead with masked implementation is like 2.4 times in terms of cycles, and the area count in a Xilinx FPGA increased by a factor of 1.3. So in hardware, actually, you have area performance trade-off, so you can play with it. You can improve the performance or like reduce the area consumption. So yeah. So basically, I presented different masking approaches and the challenges in them, and also results for a full key encapsulation scheme. Now, Yeah. The next part will be given by Prasanna. Maybe, yeah, I give the control to Prasanna.
Due to time limit, I'll just quickly take a minute to cover the implementation level attacks along with the conclusions. Yeah. So
sorry, I was muted there. Maybe just the high level, because we're about 18 minutes over time right now.
Sure.
Maybe very quickly, yeah.
Yeah. So apart from algorithmic level attacks, there have also been implementation level attacks on LWR based schemes, and the major computation blocks that have been targeted are the polynomial matrix or the polynomial or the matrix vector multiplier, the error or the secret sampler, and also the pseudorandom function or the pseudorandom number generator, which is implemented using the extendable output function such as shake, using Ketchak computations. So, and the most potent implementation level attacks are the single trace key recovery attacks, and the previous algorithmic level attacks that we saw earlier can recover the secret key only using multiple traces, but there are implementation level attacks that can perform single trace key recovery, and these are some of the attacks that have been presented over the different computation blocks. So we have the polynomial multiplier mainly targeted using single trace attacks, as well as the number theory transform, which is a basic block in polynomial multiplication. And we also recently had a paper. There was also a recent paper which targeted the shake extendable output function using a single trace key recovery attack, which primarily uses algebraic side channel attack techniques. And the main advantages of implementation level attacks are that it obviously performs a single trace key recovery, and it can also potentially defeat the masking countermeasure as well. And these attacks mostly require only side channel information. They don't really require communication with the target device, but the algorithmic level attacks that work in a chosen ciphertext setting, they require communication with the target device. And with respect to disadvantages, these implementation level attacks require some or complete knowledge of the implementation, and they're also very highly sensitive to SNR, especially horizontal noise in the form of jitter. So as a concrete countermeasure against all the implementation level attacks I presented earlier, shuffling serves as a very strong countermeasure against the aforementioned attacks, and shuffling of the intermediate operations within the single computation can actually defeat single trace key recovery attacks. So just on to conclusions and future works. So as we have shown different types of side channel attacks with very low trace complexity, we can definitely not ignore side channel security of lattice-based schemes, and there is a requirement for more analysis of side channel attack resistant protected implementations because most of the attacks have been performed on unprotected implementations. However, there are a few attacks that have been performed in protected implementations as well, but definitely more analysis is required. And there's definitely scope for improvement in improving the efficiency of masking countermeasures for LW and LWR based schemes. And there's also a requirement to actually come up with a new way to analyze the theoretical security of LW, LWR based schemes, as we know that side channel information can be used to sort of get some hints about the secret key. So in that direction, the leaky LW estimator by this particular work actually has moved the topic in a very positive direction with respect to integrating hints from side channel attacks to sort of concretely estimate the practical security of different LW, LWR based schemes. And on to future works, as we saw, we have only covered the LW and LWR based schemes, and there's definitely scope for algorithmic level side channel attacks on N-true based schemes as well. But existing work mostly covers side channel attacks targeting the polynomial multiplier block at the implementation level. But there are also several plaintext checking oracle based key recovery attacks known for N-true based schemes that work on chosen plaintext secure schemes, and these attacks can definitely be adapted to chosen ciphertext secure N-true based chems as well. And definitely there's more scope for future works in terms of coming up with more efficient countermeasures and fully masked implementations of all the different lattice-based schemes, and also coming up with scheme-specific countermeasures catering to different each and individual scheme as well. So Yeah, thank you, and very sorry for exceeding the time limit. And yeah, please feel free to ask any questions if you have any. Thank you.
Yeah. Also, our email IDs are provided in the first page. So, like, if you have any questions, you can also communicate with us directly.
Sure. Let's everyone, if you're still here, you can unmute now and thank our speakers. It was a great talk. Appreciate it.
Thank you very much. Yeah.
Thank you very much.
So I was going to let you know, during the talk, Dustin Moody's power went out at his house, and so I'm, fingers crossed the recording is okay. That's what I'll say about that.
Okay.
But I think it will be at least up to some point. So let's, we have maybe since we're over so much, maybe time for 1 or 2 questions. Anyone from the audience have any questions here? I have maybe a question if no one does. Let me just wait for a minute. I didn't see any typed in the chat during the talk, so let me pause and wait for first come, first served. Give it a couple, like maybe a half minute here, see if anyone wants to type something. While we wait on any questions someone from the audience might have, so one of the things that I think is interesting here about side channel analyses. Now, first of all, in real world scenarios, actual implementations, deployments and products, that type of thing, of course, you need to handle the area holistically and actually defend against the types of attacks that have been identified that are relevant for your application scenario. In terms of the NIST process, though, so putting on my NIST hat here, so one of our jobs is to distinguish, between candidate A and B and C and D and pick the standard, right? And kind of drive things in that direction and get the community to kind of work in that way. So with respect to the standards process, so many of the attacks that you described were lattice-based attacks that were distinguished perhaps from, things that would work on non-lattice schemes. And so, there was some kind of comment you had of like, oh, well, here's something that's very specific to lattice-based crypto, a type of attack that works here that wouldn't be present on, say, Psych or Macleese or Bike or, some of these other types of non-lattice schemes, right? So that was a very good, well-put point. One of the other questions I have there is, were there any attacks that you're aware of or any ideas for attacks that you're aware of that distinguish within the category of lattice-based systems? So the one thing I did see you mention was, you have Phroto-Chem versus the structured variants. So you mentioned, I think, at least Sabre, maybe Kyber also as well. And you said, oh, well, Phroto needs more queries. And so there's at least some small number, like less than a dozen, traces versus 1,000 traces or something like this. That's a lower scale kind of thing, because if you have the ability to perform traces, then 1,000 is not too hard to get if you can get a dozen. Some scenarios you may not be able to get a trace at all. But there, one of the questions I have: do you have any idea? And the answer could be we don't. I don't know, or there doesn't seem to be. A question would be: do you see anything that would work on, say, lattice scheme A, but not lattice scheme B? Something that exploits a particular property like structure, module structure, rounding, not rounding, intrue versus not intrue, that type of thing.
I mean the ciphertext malleability property. This directly comes from the LWLWR based PKE framework. So probably it's there in Entrue as well. But then this idea of changing only a single coefficient and changing only the corresponding message bit, this one-to-one relation is very much only for LW and LWR. So as I told in the talk, the message is diffused through the decryption procedure in Entrue based schemes, but then in LWE, this diffusion of the message is not really there. So you have the message, you're adding something to it and just removing it. So in that way, there is no sort of diffusion of the message, and that behavior is different when you compare. If I just want to say compare LWE and Entrue, and in Entrue you have multiplication that's going on that sort of diffuses, and in LW you have two ciphertexts, so you can sort of play around with it a little bit more compared to Entrue where you have just a single ciphertext Yeah, I mean, these are just minor differences, I would say, but yeah, I mean, overall, it's a difficult question to answer if there is something clearly distinguishing the two types of things.
Yeah, I think more work is needed in investigating fat channel security of n-true based. Okay. So, yeah.
All right, great. Well, so just simply because it's quite late at this point, we're almost 30 minutes past the hour. And I don't see any questions from chat.
Okay.
I guess we'll just go and wrap up here and say thank you again. That was an amazing talk. Really helpful and great survey. And very nice work that you guys have done. So for the audience, before everyone leaves here, just to say this is the for now the last of our seminar talks that we're doing for now. We're going to have the round 3 NIST PQ seminar in June. The submission deadline is April 23, which is just under a month from now. So please submit your best work, and we'll be happy to review it and have a great conference in June. So with that, thank you again, Prasanna. Thank you again, Sujoy, and thank you everyone for attending. And we'll see you in other venues. Thank you, everyone.
Yeah. Thanks for the opportunity again. Thank you. Yeah. Bye-bye.
Bye. Thank you.
Bye-bye.
Bye. Yeah.
Thank you.